Okay, so welcome back to week 15. Today we talk about nonlinear static pushover analysis. So nonlinear static analysis, we already discussed this topic because I made some examples on this in like week 3 and some other, I think, some other models that I've provided for you. It's gonna be like, I'm gonna show you 3 different models in which we developed 3 different things. On the description, I said that I was gonna talk about how to read the results, the load distribution patterns, and about how to make a sensitivity analysis by changing some of the model parameters. But in the end, I didn't have time to finish this kind of analysis. So maybe I will try to put it as something else at the end of the course. I'll just add, let's say, an additional example on how to make some parametric sensitivity analysis. Like if you have, for example, I don't know, material properties and you want to do pushover by varying your concrete and steel properties in a frame structure and see how the response changes. This can be done very easily. But we're not going to talk about it today because we won't have time. Well, welcome to the new people who have just arrived. Just so you know, the course is very short, so you'll have a lot of time for questions later. And if you're new, there's a lot of things to talk about. So I'm sure everybody of you knows what's a nonlinear static analysis, so it's not like we're gonna talk about the basics, but this is the examples that we work with in this course. We have, and let's say the examples that I'm gonna bring you today work on this kind of structure, so 3D frame with rigid diaphragms. If you want to do different types of structure, then let's say the load pattern application will be different, not more complicated, but just different ways to do that. So there we have 7 stories, 7 constrained nodes that defines our rigid diaphragms movement at the center, and those are the points of applications of our load pattern for a pushover analysis. There's 2 ways that nonlinear static analysis can be carried out: load control and displacement control. We already discussed this in week 10, but just to reiterate, in load control, the users, so you guys, define how the loads will be incremented over time. Instead, sorry, just one sec. Yep. Instead, if you're doing a displacement control, it's the integrator, so the type of integrator that you're choosing, displacement control, that will define how the loads are incremented over time. What you're actually defining is just a target displacement that you want your structure to reach, or you expect your structure to reach. So in displacement control, in load control, you assign, let's say, a load, and then increment that load for the duration of the time series that you want. So for the typical thing that is done is that you say, okay, I expect for my reaction at the base to be, this is very easy to calculate if you have to define if you have a test of reference, if you've done some experimental testing of reference and you know what's the capacity of your structure. So you input the maximum capacity of your structure as an applied load and you do load control. There's another thing that you can do with load control, which is a kind of displacement control, which is using the load control integrator, but applying an applied displacement, so an FP here. And with this applied displacement on the top of your structure, you apply a displacement with the value of the maximum displacement expected at the top of your structure, so the maximum drift of the top. And this way, it will be a kind of displacement control, even if you are using the load control in the integrator, because what you're actually asking the integrator to control is the top displacement. So it's a bit of the same as asking to control the displacement. The point is that this does not work if you want a force profile application, because as for displacement control, in this case, the applied load has to be in one point. It's not something that you cannot control the displacement of more than one point in this kind of analysis, okay? So when you want to read the results of this kind of analysis with this application of applied displacement, you kind of read the, sorry, there is a typo here. Yes. So you read the sum of reactions at the base as the maximum load capacity reached. So this is what you are going to look for inside of your results. But I mean, this is not always the case. So if you have a column, you can do this. But if you have a structure, this is not going to be most the case of load pattern application, because we don't really want something applied at the top. We want something applied at each story. So if we're doing displacement control, what we actually can do is apply a lateral load equal to 1, set a target displacement has the maximum displacement expected, and then read the load multiplier of the structure, so the time. And that time is actually the maximum capacity reached, because we applied a load equal to 1, and so the load multiplier will be actually my actual load maximum capacity reached. If you see, this is the plot of a monitor. So in this case, I'm not reading the time, I'm actually reading the reaction forces. But if I were to read the time against displacement, here I would have anyway the same value, because I had applied a lateral load equal to 1. Just like a little note, if you are using the penalty method, we've seen in like some testing that if you use 1 and the value so of the load is very far away from the expected value, you can have some numerical problems. So just in that case, you can multiply that 1 for the ordinal magnitude of the result that you expect, especially if you're modeling in Newton. And so you expect, like, I don't know, to the power 6, to the power 7 results in terms of capacity. So a few thousand kilonewtons, then just try to adjust that 1 value. And you can do that just in the load pattern by applying a factor. You don't need to change the value of the actual applied force. So what's the main difference, and why do we always use displacement control? Because as I said, this case has some limitations. This is because in a like generic pushover curve, what we want to actually capture is the post-peak behavior. So we want to see when is the structure going to fail, and so what's not just the maximum capacity in terms of reaction force, but also in terms of displacement. And we will not be able to reach this point if we're using a classic load control with loads applied at each of the story, because an increment of load will never reach this point after having like reached a higher point. The load can never go down if you're controlling the increment of load. Why is this case different? Because the difference here is that you apply this an applied displacement, and what can happen in this case is that the displacement will grow, but the reaction can go down, and the kind of load that the analysis is controlling is the reaction. So let me find, okay, sorry guys for the interruption. Yeah, so I'm just gonna repeat this last point. If you're doing a load control with an applied displacement with 1 single point in which you have an applied displacement, you can manage to capture this kind of softening of post-peak behavior. This is because you're controlling reaction forces and not anymore, you're reading reaction forces and not the applied load anymore, and those can go up and down. Instead, if you're doing a classic load control with an applied force, this post-peak behavior will never be captured. So it happens all the time that we receive like, and this is not just for pushovers. I mean, it's nonlinear static analysis in general. If you're trying to push a beam from an experiment down and controlling the displacement of the center of the beam, and you're doing it by an applied force and with load control, you will never see the decay of the response in the global response, because the load controller cannot do that. So after this kind of premise, I can show you a few types of pattern application that can be done in STKO. So what's the most easy thing to do is to apply a constant force distribution in each of the master nodes. Why are we doing this here? I said this at the beginning, but just to repeat, this is a frame structure with rigid diaphragms. And so it makes no sense to apply the force in any other point than the central point. Because of course, this central point will actually dictate the displacement and rotation of all the points on the same plane. So the simple thing you can do is just apply a constant distribution of forces. Otherwise, you can go further and try to apply a triangular distribution of forces. A very easy way to do that is to just like use the function mode in the node force application. And I mean, we discussed this in week 3, but just to remind you guys, and divide the zeta coordinate of the point to which you're applying the force to by the total height of the structure. So this is just, in the end, is gonna be a proportionate to the zeta height of the structure and of any, of not any entity specifically, okay? And then if you want to go forward, there's like 2 specific types that are mostly used in literature, which are the modal and the mass proportional and load pattern distribution. Yes, lateral load, lateral force distribution. So in this case, we don't have yet like some explicit tools, X-objects tools that you find in the work tree to do this, but it's possible. And it's possible through TICO scripting. We're planning to develop this TICO scripting into some X-objects that you will be able to just pick from the tree and add to your analysis as specific load patterns. But in general, it's already doable. You just need to know how to code it. So I'm providing you guys some code that you can use for this kind of structure to develop these 2 distributions. So in this case, each constraint node at each floor is going to be pushed with a force that's proportional to the eigenvector of the principal mode of the structure. So I mean, this I did in advance. So I did an eigenvalue analysis of my structure. I saw that mode 1, actually mode 0 in the index place of STKO. It's actually translational in the -x direction. In the -x direction. And so these eigenvectors were extracted from the results and applied to the master node. And I'm just gonna show you how, and it's really, really easy actually. So let me just take the reference model. So the first thing you need is to have a master node selection set. So because all the constraints node for each floor are included in this selection set. So one tool that it's quite easy when you're doing some custom TICO commands and other things that you need to know the ID of specific elements and you need to know it quickly. It's not like you have to turn this on and just kill yourself. So you can create something called a region command. Select the selection sets that you are actually wanting to extract the nodes from, the nodes IDs from. Select nodes and then write on list master nodes. So these master node lists will print actually the nodes. It's something that it exists inside of STKO and OpenSees. It's not something that is gonna be outside somewhere, saved anywhere. It's just something that you can recall from a different custom script. So once you do that, we developed, with a lot of help from Massimo, this small script to define a model proportional load pattern. There's some input parameters that have to be defined. It's very short, as you guys can see. So first we set the DOFs, so the degree of freedom in which we want to apply our pushover, and we say in the X direction. Okay. Then we define a pattern tag. So we already know that in our analysis, there's another pattern, which is the gravity analysis pattern. So this one. So we define another tag, which is gonna be 2. You know that as STKO writes the TICO scripting, it will not refer to the tags that are here, but it actually will refer to the tags that are required in OpenSees. So in OpenSees, whenever you create a load pattern, you need to number them starting from 0. Of course, if you skip one, nothing happens, but still, you need to number them starting from 0. So we already know that this will be numbered as 1, this one, so we would number it as 2. Just so you know, it would be a cleaner code if we had written like a kind of an if that said, if there is no pattern tag, take the number 0. If there's a pattern tag, write number 2. But I mean, I didn't have time to do that. So, and second of all, we actually have to refer to the tag of the time series because any load pattern is time series, and we know that we have a RAM, so we put that. Then we set like a reference load value that we can use to increment or decrement the value of the eigenvector we want to apply. So just if you, for example, if you're using penalty, you will want to increase this as much so that you will avoid numerical errors, because you know that eigenvectors are all qualitative values and they will have very small, a very small order of magnitude anyway. Then we set the reference mode that we want to extract the eigenvectors from, and it's the same. This is something that we did fast, and let's say just for the specific model. But in the same case, as you know, when you do a model analysis, you extract the mass. So if you know which is the DOF, we could write a little script saying scan through the modes and then select the one with the most participating mass in the X direction and take the eigenvector from that node, from that mode. So it's an additional thing we can do. Actually, let's write it down. So add scan of calculated modes for selecting more relevant in the DOF direction. And same for this, scan for existing pattern tags. Okay, then what's done later is just defining a load pattern with these tags that we defined in the input, and then saying, okay, I want the eigenvectors at each node that it's in my region master nodes. So this is what I defined before, and I can call it here as a variable. So the region command just defines a variable with that list of IDs inside of OpenSees. So it's the same as writing into your STKO script set variable with that list of numbers. Okay. And then I want the eigenvector of those nodes in the direction of the DOF that I decided, but I need to add one because this is in base 1 and not base 0. Okay. Then I want to define a factor to multiply that eigenvector for and assign that value to a value of load. The value of load needs to be the vector of applications of my loads needs to be of the size of the number of DOFs of my node. So let's say it's at the same length of the eigenvector that I'm extracting. And I want to take the NDOF number 0 from that from that eigenvector that I extracted B. Okay. Then I set in this P vector the value of P at the exact DOF that I want. Okay, so inside of my node, this is the same as defining a node load. How is it called? Wait, I don't remember. Load pattern, but I think it's node load. Force, node force. It's the same as going here and saying I want this of this tree. I want to take this one and assign something here. So you have to create a vector in which we assign the value of the load that we define for the factor. The factor is the eigenvector for this reference factor that we defined before. And then put this load everywhere in each node from this vector. Of course, the nodes from the master nodes, not any other node. This is just the same as going here and creating a node force, like as if you, I don't have now the run analysis, but anyway, if you open the MCO file in HDF5 viewer, you can see the eigenvectors for each of the nodes that you want. And this is the same as going there, takes the value, put it here, adding a node force, selecting the node and doing that. So this script does exactly the same thing. With this, we can create a load pattern that will look like this one. This we obtained by, as a test, we fixed the master nodes and then plotted the reactions at those nodes, because of course in reality they're not fixed, but this is what we are actually going to obtain as a distribution of forces. The same can be done to have a mass distribution of forces. So in this case, I applied a different mass, decreasing mass at each floor, just as an example, because of course I didn't calculate the mass for each floor, and most of the time it would not be with such a difference, but I wanted to see if it worked, so I did the same. I applied a different mass at each floor. Let me show you. So each floor has a different mass. As you can see, like floor number 1, floor 0, etc. Okay. And then same, we need our region to extract the master node IDs. And we go inside, and this script unfortunately is a bit longer, so it's a bit more complicated, but not so complicated. We have the same input as before. Then we have to define a number of floors that of course will be the same as the length of our master node list, and create a placing variables getting all the IDs of all the nodes in our structure. Because in this case, we don't want anymore to extract some result from the previous eigenvalue analysis, but we want to extract a condition application. We applied masses to our nodes, so we want to know how much mass there is in each of the levels. Of course, this starts from the assumption that mass is just in the nodes, okay, and that you assigned all the mass through the node mass or the phase mass or the volume mass command. Because if you apply the mass through the raw, that can be inside of, I don't know, some shells or some specific materials for 2D and 3D analysis, that will not be computed in this way. So this is just for node mass, or let's say generally for mass that is applied as a condition and not through a physical or element property. So we have a mass value for each floor in the desired DOF. And then we try to find, first we find the zeta coordinate of the master node. Then we find all the nodes in our structure that are placed at the same zeta coordinate with a tolerance of 1 to the power minus 8. And we put them in a list. Then we calculate the mass of each of these nodes, and we sum it to let's say a mass that will be calculated for each floor, okay? And for each floor, we put that mass in a list. If you want to normalize, we added this little thing that is not in the previous, actually, in the previous script, that could be added there too, which is in the sense that if I want all my forces to be add up to 1, then I know that I see my load multiplier in my pushover has the time, and that time will be exactly my capacity in terms of force. But if I don't normalize, then I need to multiply that value for the sum of all the loads that I'm applying to my structure. So to normalize that, I do these 2 small loops. I mean, this is really easy. And then as the same, I create a new pattern, a new load pattern with the tag and the time series as before. Sorry, again, the tag and the time series. And for each node in the master node, I'm going to apply, first create a placing vector with the same length of the master node DOFs, which is always 6, because if we have nodes in 3D, they always have 6 DOFs. And then I'm going to create like our mass application has a load and insert it as a node for each node of the node ID of the master nodes. Okay. And let's say this will result in as I showed you before, a distribution like this one. This time maybe sounds a bit complicated because, I mean, for me, for example, it sounds a bit complicated because STKO is always a bit complicated, but it's very powerful. And this show you that you can do maybe things that are automatic in other software that you just like scroll down, you say, I want a mass distribution pushover, and that's it. But then you never know what's happening behind the scenes, and you cannot control very well which mass is being like taken into account, which actual mode has been taken into account, if you have any specific threshold that you want to set. So this is just to show you that STKO is hard to learn, but very powerful. And the same with STKO interface, you can do things that maybe by hand were gonna be a bit more cumbersome. So just to end, like, I'm sure you guys know already this, but because it was already in some of the slides before, what you can do to extract results, you can go into the post processor and just like extract results on the nodes, let's say reaction forces, and sum them at the base, and then results on the top, displacement, maximum displacement at the top nodes. But you can do this through the monitor too, just like you have to create some selection sets for all of your base nodes. Base nodes like this one, and in your top nodes. Yes, and so of course we know that maybe this will move the most, but if you have a irregular structure, then you're not so sure. So you just select all of them and then select the operation maximum for the displacement and sum for the reaction force at the base, which will represent my shear capacity to this kind of lateral load distribution that I defined. So I don't have a graph that shows the difference between this different distribution response, because I didn't have time to do it, but I was thinking maybe it's interesting to do, so I will try to add it to the presentation. But for that, then that's all for what I have to add about, let's say, pushover analysis. I don't know if you guys try to do any kind of pushover, if you have any already experience with that. If you want to add something to the topic, because I'm sure if you have already experienced, you can kind of add some information.
I have a question.
Yeah, tell me.
In the slide 11, in this case, the graph you were showing was like the monitor you were showing was the reaction force. So we do the sum of all the nodes we have in the basement, let's say, and then on top you were plotting the displacement of all the nodes at the same time, but asking for the maximum.
Yes, so it's as if you're plotting the displacement of one node.
Oh, but the thing is it possible? Well, you have a diaphragm, a rigid diaphragm.
Yeah.
No, because like sometimes when I have multiple nodes, I don't know what to put there.
If you don't have a rigid diaphragm?
Because, so, yeah.
As a control node or as a result plot?
Because I normally have the control node. Because, for example, when I do just the pushover with my experiments, I only have one point that I check, which is the displacement. So in that case, doesn't matter if I put some maximum or wherever. Because
yeah,
as a default operation is always sum.
Yeah, the point is that just like if you see here what I showed before about the control, how does it work? So displacement control works that displacement always increases. That's how it can capture things like this, because displacement can move up and down in terms of corresponding force, but anyway, displacement always increases. I don't know if you guys remember, I don't know if I have it, to be honest, let's see. No, well, I can take it from the internet later, but if you have snapback or if you have any other numerical phenomenon, you cannot capture that with displacement control. So what you got to do when you pick a control node is choose a point that you know will always move in the direction of your analysis through time. So it can also be not the place where you have your, I never know how to pronounce this, strain gauge, like where you have your control, like the place where you place physically in your experiment the things that control the analysis.
Yep, but the thing is, if I don't do that, I cannot compare exactly with my experimental graph.
Yeah, I mean, but if we should do that in your experiment, it means that you're sure that that node will always move forward, no?
Yes, well, this is the thing, it always moves forward. So, but the thing is, in this case, in the experiment, I have one point only, and I always monitor this point, and so it doesn't matter what I say is one. But then I was doing this like something similar to this, but in a smaller scale, because I was trying to calibrate, and so I was choosing a point, and then I did this because you always do this collection of nodes, and then I was doubting if I put maximum, if I would have like a node like this maximum was like being picked from a different node each time or something like this. I was afraid of something like this happening. I don't know if I'm explaining myself.
You use the a collection of nodes only if you know that they move more or less all in the same direction. So like if you're afraid that or different direction, then don't like just pick one node and that's okay. That's anyway describes the.
Because for example, in the slide 7, in this case, because your structure is not completely symmetrical, this horizontal displacement in X actually has a bit of rotation.
Yes.
So this sometimes what I think is if I put maximum, I won't actually know which is the node that is actually moving. I would have like to go one by one, plotting to see which is the one that moves.
Okay, but what you can do is, for example, if you go in the let me take I have to go take the file because there's still people coming in. You guys cannot see my computer, no? Just the presentation. Wait. Yeah, you can see it now. I'm gonna just open the result file that I have. Because what you can do is is this something that you want to do to pick the control node or to just pick the node to plot the pushover curve? Your mic is off. Your mic is off.
Sorry, I turned it off because of the sound, the noise here. The thing is, what I'm afraid is like if I have my control, like if it's better to define one control node, even though it's not the place where it moves the most, or it's better to just like say, okay, I have all these points and I'm looking for the maximum one and I don't care with this.
No, so there's a different thing. So if you put the control point in a place that it always moves forward, but then some points move the most, they can move more than the point in the analysis.
Okay.
Of course, you say I'm controlling the displacement of this, so I'm pushing this point forward, and this point will move to the target that I gave. So how can other points move more? I mean, if places detach, they would just move more or in a direction. So the fact that you pick a specific control node does not change the way the other nodes will behave unless you have, as in this case, rigid diaphragms. So all the nodes in each plane, they move the same. But for example, I don't know if you, here you just show the nodes. I mean, this will not work here, but you can extract on the nodes of the stage of the pushover, the displacement in the X direction of all of these nodes, displacement, then you keep them separate. Of course, now here, they're all the same, okay? Because they're all on the same diaphragm. But in the end, you will have different, like if you have a structure that does not have a diaphragm, they go in different directions. And there you can just go and look which is the node that moved the most, for example. And
okay, so I can plot, yeah, all of them, but okay, it will be plot against the steps.
The time, yeah, you can plot it against the time. You can also just copy it in Excel and just select
and check which is okay, and then I can run it again, taking which is my, well, let's say not in this case because it's a rigid diaphragm, but I can check which is the one that is moving the most and then run again, taking that as the control node, for example.
Yeah, exactly. But anyway, I mean, if you also see the deformation, you will just guess which is the most moving node.
Yeah, okay.
Anyway.
Thank you.
There's many people who joined as we were talking already. So I don't know if any of you guys wants to ask any questions. We can go through some of the parts of the presentations again. If you ever did like pushover analysis before, if you have, if you found any specific like problems.
There is a question in the chat.
Oh, thank you. I didn't see that. Is gravity analysis a prerequisite before pushover? Well, it does not make sense not to put it there, to be honest, because it's not like you are going to analyze a structure that is not subject to its self-weight. It's not something that you need to do, but if you're doing nonlinear analysis, so your material is nonlinear, and you want to account for the effect of the gravity loads, then you need to do that analysis before. Otherwise, you're actually just assessing the lateral capacity of your structure based without the damage or anyway the stress distribution that could occur if you actually analyze what's happening due to gravity load. So in my opinion, it is just conceptually. It's not. It will run. It just doesn't make much sense not to put it there. You're welcome, Faisal. Welcome to the course again. If anybody else has any more questions, you're welcome to ask. Following that question, sorry, I think you already explained this in another week, but instead of if we add to the nodes all the mass, let's say we calculated the mass of all the building and we distributed in the nodes, and we apply it as a mass load. This is like, and we don't have vertical loads, just this mass nodes. Mass condition, you mean? Yes, sorry, mass condition here. Like you compute the whole weight and then you put it in the nodes, and you don't add any extra vertical load, and then you do the analysis. You can do it with these masses, the vertical analysis. No. So mass and weight are different concepts. So you cannot do any kind of static analysis with masses. We have masses here because we did eigenvalue. Eigenvalue needs masses to work. Otherwise, we would not have needed any mass in our models here. To do pushover static analysis, you don't need masses. I remember the class. Sorry. I just had this question and it was a doubt, and now I remember the class. So yeah. It's just a common mistake. Also, it's like static analysis, if it's static, that does not need any mass because there's no inertia considered. Like anything that's transient has inertia, so it needs the mass definition. Anything that's static needs the weight. And if you don't decide the weight, you will not see any result based on that. You have someone in the waiting room again. Oh, okay. So, any of you have any more questions that you want to share with us? Anything that you've been doing in OpenSees that could be useful to also the others? If you want to complain about something the software does not do for you, I always do that every day.
Hello to everybody. Thank you, Francesca, for the nice presentation. I'm using STKO, and it's been very helpful, your your videos and also previous videos from Professor Petraka. I am doing analysis in masonry structures, and I'm having a problem regarding during the analysis. When I run, I have a message that says that error fracture energy GF is equal to 12,000 is too small, or the element characteristic is too large. I've been working with modifying the parameters of the energy, but the problem still remain.
I think I will ask Larissa to answer this question. Your mic is off.
Yes, yeah, I ran into this problem like every 2 or 3 days. You have to or change the size of your element, or actually you have to see if you don't have a mistake in the units of your fracture energy, and this is why it's really small, and so you have to calibrate it until it works, until it runs. Normally, in my case, normally it's like I have always 2 orders of magnitude less when I do all the conversions between newtons, kilonewtons, millimeters, and meters, and then after this it runs.
But so what the error is telling you is that you're asking the fracture energy that your input to break an element that's too big for it. Okay, so the calibration does not work because it's as if you're saying to a very large specimen to fracture with a very small fracture energy.
Okay.
Should either like shorten the length of your elements or increase the size of your fracture energy.
So shortening, you mean by that reducing the mesh size once I am meshing, right?
This happens because you use domesticity, the auto regularization option. If you, for example, you already know that your specimen was of a certain length when you obtain the fracture energy experimental result, you can regularize your own fracture energy, but then you have to be careful of what size of element you put in your
okay.
So anyway, if you Google on the forum the fracture energy, you'll find like a lot of Larissa's questions.
Yeah. Actually, I found.
You will find all my questions.
Yeah, I found your question. That's true. Yeah, I have it here. Yeah, it's the same thing as mine.
Okay.
Yeah. Thank you very much.
You're welcome. What kind of things are you modeling with domesticity?
Well, I need to do homogenizations of masonry to prove the accuracy of a macro element. So I'm using Lagomarsino's Trimuri, and I want to prove the accuracy of the Trimuri model using a homogenized model. So yeah.
Okay. And are you getting good results or not?
Yeah, actually, I had a bigger wall and the results were very nice. I didn't have this problem, but now I'm building a small pier with 3 bricks and testing it, and then I had this problem. So yeah, I think it's something related with the units because the mesh is actually very small. I used 2 millimeters mesh, so I think it's very small.
So maybe
but then
it's like Larissa says that the order of magnitude of your fracture energy is not right.
Yeah, that's the problem. Yeah, that's true.
Well, the thing my main problem always is that this fracture energy, I have it from like, you know, someone else with experimental campaign. So then if you have some experimental curves from your units, for me, this is what was like a game changer. Like I managed to get these experimental curves and then work with them because of the auto regularization thing. Then if you distribute it in the length of the specimen you have, then you will realize that the value they were using was really small than the one that you should be using.
Good.
Yeah.
It would be nice to see the results of your models. So maybe you should either post them on the forum, or we should try to find a place for anybody to show their work with STKO, because it's really interesting that you're doing something like that. So it's a combination of software and you're trying to validate one model with another. So I don't think many people are using STKO for that. So cool.
Yes, I will. I can upload my once I fix it, I will upload it to the forum.
Good.
Thank you.
You're welcome, and thank you for participating. So we still have some like 10 minutes, actually even more. So if you want, oh, there's something. Thank you, Francesca, for this section. Yeah, I don't know. So it depends on what's the question about. If it's about meshing or some things that I can help you with, or if it's just specifically about how to model physical and element properties for SSI, then no, I cannot be of help so much. I have to study myself.
I always have questions.
Wait a second. Is there a script that combines the contribution of all modes and applies it as a load pattern? Hi, yes. I don't know if you got here late, but we described this exactly today. So I'm just going to show you my presentation again. To do model proportional lateral load distribution for pushover analysis, we said that just for this structure, we developed this little script in which first you have to define a region of the nodes of application of your distribution. In this case, we have a 3D frame structure with rigid diaphragms. So we only apply the loads to the nodes at the center of the diaphragm. And then we create a very short script in which we define the pattern tag, pattern time series, reference factor to multiply the value for, and then extract the eigenvectors from the first mode and assign it as a load. So your specific question, I think, was about how applying the contribution of all the modes has a load pattern. So to do that, I'm sure it's possible. You can start with that script and extract contribution for all the modes and then combine them in a way that you think is best. I don't know which is the way you want to combine them as I don't know, to extract all the maximum in each directions, or but of course, pushover analysis is mostly in one direction. So I would say maybe you want to combine the contribution of the modes in one direction, or you want to make different load cases and analysis for each of the modes. Like, what's the objective of combining the contribution of all the modes? Thanks. Okay. Okay. Well, I mean, if I answer your question, okay. I was curious to know what was the objective of combining the contribution of all the modes. Maybe you can select all the modes that are relevant in one direction, so the ones with a certain percentage of mass participating in that direction, and then combine those, which would make sense because maybe in X, it will not be a triangular distribution all the time, but it could be a different kind of distribution. So that's also interesting to explore. Larissa, you said you had another question.
Yeah, but it has nothing to do with this
Okay.
class. Because I'm still working with the embedded element.
The what?
The embedded element. The one like, so if I have a solid, a 3D solid, and I have a shell, and I want to move like together.
We have a lot of new posts about that. Do you see?
No, okay. No, because I've been working on something else, and I've been having this problem, but I don't want to post because I don't know actually what is going on.
Because that's just like that Massimo figured out a way to better calibrate the value of the penalty. That it's not in the description yet. In the description.
Okay.
So I can point you to that if you want.
Yes. Okay. Then no, perfect. I will read this, and if I keep on having this problem.
And if it's about how to calibrate the penalty value, then we have better information now.
Okay.
If it's about something else.
No, it's because like it runs everything, like everything looks okay, but then the results are really weird. And I don't know if maybe it's the penalty value that I have to calibrate better, or
So just I tell you what we do.
okay.
First thing you do, you put your model linear. So you put all materials linears, no correlational, no p delta. You put your model linear, and then you put the embed value that you think you should put, and you run the analysis, and you see what's the norm. So the norm is the error of your analysis, no? And if the model is linear, it should be very, very small, to the power of 14, minus 14, minus 16, so very, very small number. Then if that's not the case, something is happening. So it means that maybe the embedding value is not right, because you excluded any other reason from the model to have a big error. I mean, nonlinear properties, they create errors in the conversion. So you can have, you cannot distinguish if that's coming from the embed or from the nonlinear properties. So you do that. And another thing you can do is that this penalty value, you can define it based on the mesh size. I know that in descriptions, it says that it's independent on the element size, but if you are in 2D or in 3D, the things changes a little. So what you can do is that you take your largest stiffness, you multiply that for 100 to get an extra 2 order of magnitude. And then I think you divide that by the size of your element. So if you are in 2D, by the size, if you are in 3D, by the area of your element. And that will be
okay, this part is new, because until the 100 I was there.
And this value that you obtain from this operation, so per 100 divided by the size, it gives you the order of magnitude that you have to apply to your penalty value. So the power of 5 to the power of 6, and it's normally a bit smaller than what we were applying before. Before we were just multiplying the value of the stiffness for a certain order of magnitude. This is does not mean that what we did before was wrong. It's just that we get better results with these kind of parameters, which are smaller. Because with the penalty works that you're actually inserting very high stiffness values into the matrix, no? And if we have smaller values, we can obtain a better stability of our model, because we have smaller numbers and those numbers have less error. But if you increase the size of the number, then you can have an ill condition problem and etc. So the point is that this works a bit better, and it's actually related to the element size. We have to update the documentation about it.
I will try this, and if the thing I have that is weird keeps appearing, I will post it and try to explain myself as much as I can, because I don't know what is going on. Okay, no, I will read the new post then, and I will try this new thing.
Another thing that I think we don't explain people. So for the mesh, you have to mesh your retained geometry with a smaller element size than your constrained geometry, and that's okay. But what we notice is that it's also very useful if those nodes, they don't coincide. So if you have a beam, which is a face, and then a bar, which is a line, it would be nice if the element of the face kind of like ends up in between that line and not aligns with that line. I don't know if that's
yeah, I understand, but how can I, like, well, the thing is, mine are a solid and shell, so both are square with the same dimensions. How can I make them not match?
I mean, if you put yourself in a plan and you see what's the height of your beams, and then you kind of, I mean, of course you want maybe an element size of a specific number, but if it's not 15 but it's like 14, nothing changes really. So just like play with the global mesh size and see if you can first align the beams that represents the bar, let's say in the middle of the solid mesh, and then assign the smaller seed to the bars.
Okay, I will try.
Thank you. Refine thing, but we noticed that it's better.
Yeah, the thing is, if I refine too much, because the shell I have, if I refine it too much, I have this error that I don't have enough space to run it or something like this. is too big or something, because I had this error and someone said that it's because it was too big and what the mesh was too fine.
Work array is too small.
Sorry?
It says something like work array is too small or something like that.
No, it was something about the memory or
Okay.
it was something like this because I did it really small. And
Not exaggerate, start large.
yeah.
And
Okay, I will try. Thank you.
okay. Anybody else has more questions? We still have some time. Otherwise, we can meet back next week. I'm glad there is like more people coming in today. I hope it was useful for you. Thanks to you, Salam. And thank you very much, everybody, for participating. I will try to complete the presentation this time instead of just uploading right tomorrow, because I want to put the comparison between those lateral load pattern distributions. And I'll see you again next week. Next week, we talk about nonlinear time history analysis. We need math for that. And yeah, so I hope you guys will be able to join again.
Thank you, Francesca.
Thank you, Larissa, for your question and for coming. And if anybody, yeah, just thanks you guys. Thank Oguzhan, thanks Odin. Thank you, Antonio, for participating. Thank you, Hernan. Thanks, Faisal. Thanks. See you next week. Bye.